Hello and welcome to the Semiconductor Industry Association's public webinar series, where we address many of the key issues facing the semiconductor industry and the global market. My name is David Isaacs. I'm the Vice President of Government Affairs at SIA, and I'm here to introduce the webinar and get things started. Today's webinar is a collaboration and part of an ongoing partnership between the SIA and the Semiconductor Research Corporation to discuss the Decadal plan for semiconductors. We've covered many of the seismic shifts identified in the Decadal plan, and today our focus is on communications challenges facing the semiconductor industry. So, as you know, the Decadal plan is a framework that describes the possibilities for semiconductors in the coming decade and defines the key challenges that must be overcome to realize those possibilities. So the Decadal plan cites 5 seismic shifts facing the industry and semiconductor technology. And one particular challenge is the imbalance between communication capacity and data generation rates. As everyone knows, we live in a world characterized by always available connectivity and communications with tremendous impacts on the way we conduct our lives and our economy. And the ability to get data from anywhere and send it everywhere has transformed the way we do business, our lifestyle, and our personal habits. But as a result of that lifestyle change, we require new research directions to address the imbalance between communication capacity and data generation rates. So, to get things started, and before we turn to our panel of experts, let me introduce Rafiq Maki, head technologist of Mubadala Capital Ventures. And with that, I turn it over to you, Rafiq, to begin your presentation. Thank you.
Thank you, David. Good morning, everyone. If you're on the West Coast, good afternoon. If you're on the East Coast, good evening. If you're somewhere else. It's truly an honor to be presenting the Decadal plan and the emphasis today on new trajectories for communication. You know, the Decadal plan is a truly significant document. It's been developed by a committee of over 40 engineers and scientists, meeting weekly for the past several years with quarterly workshops and bi-monthly webinars. All under the leadership of SRC and my good friend Victor Zernov. Many of the slides you will see today were developed by the Decadal Planning Committee and by SRC specifically. And so with that, let's go to the next slide. I'd like to start by talking about data. Why data to begin the discussion today? Because data is now so critical to companies, it's critical to the government, it's critical to society in general. Data shapes our opinions, data drives our decisions, and data drives our actions. And from the point of view of the Decadal plan, data has major implications on storage, it has implications on the way we compute and analyze, and it has implications on communications. And if you look at this chart that looks at data storage over time from 300 BC all the way to today, it's really an amazing chart. And you can think of it as a key measure of human progress, you know, reaching 10 to the 14 bits per capita today. Now, I'm old enough to remember a billion, you know, being a huge number that I can't even conceive. Trillion, you know, unbelievable. But 10 to the 14 bits per capita and growing exponentially. In healthcare, for example, it is estimated that the amount of data produced is doubling every 6 months in healthcare. So data is truly critical. And if you go to the next slide, if we overlay bits stored over time with the world GDP over time, you see a very interesting correlation between the two, reaffirming the statement that data production is truly a key measure of human progress. Next slide, please. And data, of course, is produced, and we have to communicate this data. And if you look at the communications field, the communications industry, it's truly changed the world. Going back to the first major wave, and I'm skipping over the printing press. I didn't want to go back that far, but if we look at the first wave as starting in the 1840s with the telegraph, the telephone, the phonograph, to the second wave, which in many ways was ushered in by somebody who doesn't get his due in the history books, which is Reginald Fessenden, who developed amplitude modulation and made possible radio broadcasting, to the third wave, with Sputnik, the ARPANET, and the beginning of mobility, in my mind, with the calculator, the handheld calculator, and my favorite device of all time, the Walkman, which I still love to use from time to time. And of course, the ARPANET and what it has made, and the first cellular phone developed in the early 70s by Martin Cooper at Motorola. And it's been said that the first cellular phone call ever made was from Martin to one of his competitors at Bell Labs, Joel Engel, as a prank call. And this has ushered in the fourth wave, which we are benefiting from today. And if you look at the fourth wave and the innovations over a very short period of time, 2G, for example, 2G was 12,000 times faster than 1G, right? And all the way to 5G today. We are living in incredible times, mostly thank you to the communication technologies we have today. Next slide, please. And communication technologies don't exist in a vacuum. They are anchored, they are based on perhaps the greatest, in my mind, the greatest disruptors of all time, which is the integrated circuit. And the integrated circuit has had an immense contribution to humanity. Next slide, please. But the integrated circuit and semiconductor technology in general is facing one of its toughest challenges, perhaps the very toughest challenge in its history. We know that the traditional scaling, so-called Dennett scaling, stopped many years ago. Device shrinking is still going on. We've killed more many times over the past 5-6 years. Moore's law is still very much alive, but it's going to come to an end, and it's predicted that device shrinking will reach the fundamental physics limits sometime this decades. ICT energy trends, as we'll see a little later, are becoming alarming. And so, we're going through these major, toughest challenges in the history of semiconductor technology. And yet, at the same time, the demand is growing exponentially. We're witnessing an explosion of data, and this explosion is exponentially increasing. And as I said earlier, it has a number of key implications on storage, analytics, and communications. And so the SRC and the SIA were thinking about that several years ago. And the thing is, look, the current hardware-software paradigm in ICT is about to reach its limits. Shall we wait until it reaches its limits, or should we do something from now? Or now, some people say, look, we're exaggerating. We're not going to have a catastrophe in terms of semiconductor technology in the next 5 years or the next 7 years. Or some people disagree and say, no, it could be sometime this decade that we will reach an end in terms of addressing the exponentially growing needs of society. But the idea is, let's not wait until we hit the wall. Let's start planning for it from now. And the best way to plan for it is to motivate the R&D in universities, R&D in industry to begin to think differently. And so the Decadal plan was born out of this thinking. Next slide, please. And the participants, as I said earlier, over 40 engineers and scientists from industry, meeting on a weekly basis. Typically, we meet on Friday mornings. We've been doing this for the past 3.5 years, I believe. Next slide, please. And there are two main objectives to the Decadal plan. First, identify the trends that if these trends were to continue, they would become problematic, and not problematic on a small scale, but problematic on a grand scale. And the second objective is identify fundamental goals and targets that will alter these trend trajectories that might become, problematic in a major way. And we were guided by a key principle that we wanted to stay agnostic to the actual approach. So we wanted to identify the what, but not the how. But that's not to say that we didn't discuss possible research pathways, quantum, neuromorphic. We did discuss these, but we didn't want to. We don't want to say that quantum is the right answer or neuromorphic is the right answer. But we wanted to say that we want to see certain targets in terms of metrics like energy per bit or binary throughput and so on. So the emphasis is identify the what, but not the how. Next slide, please. And so the Decadal plan was born in and published in late 2020. And it followed a history of technology forecasting and road mapping, beginning in the early 80s with the SRC 1.0, the 10-year goals, going all the way to the late 90s with the International Technology Roadmap for Semiconductors. And I tell you something, I was a professor then, and the ITRS was an absolute marvel for us, because what the ITRS did was to bring together R&D, universities and industry, all working towards common targets, right? Under the umbrella of a common technology roadmap. And out of it came significant breakthroughs over the years. So the 2030 Decadal plan was born late last year, and it calls on something very important, a 3x increase from about $1.7 billion in federal investments in semiconductors to over $5.7 billion. Now, going from the 1980s to today, going from SRC 1.0, which is all about 2D scaling, to SRC 2.0, well, what shape would it take? Is it going to be 3D? Is it going to be something else? That's to be determined. Next slide, please. So as David said, the Decadal plan identifies 5 major seismic shifts: analog, deluge, memory storage, communication capacity, ICT security challenges, and total compute energy. Let's take a look at briefly each one, revisit each one. Next slide, please. On the analog data deluge, if you look at the chart, I love this. I really love this chart. The green line represents the total human data consumption as seen through the eyes, right? So all the data that we see through the eyes, which is like 99% of the data that we perceive. And you can see that there's a crossover that already happened between the red line, which is the data produced from all the sensors all around the world, and our total human data consumption, our maximum total human data consumption. So already there's a crossover. So this is a seismic shift. And the reason is that the total analog information generated from the physical world has already surpassed our collective human data consumption limit. So how do we address this? We address this by smart sensing, by borrowing from biology in terms of data compression. Next slide, please. Seismic shift number 2 has to do with data storage capacity. It is estimated that by 2040, we would be producing about 10 to the 7 kilograms of wafer grade silicon if current trends continue, right? However, because of the data explosion, it is estimated that we're going to need 10 to the 10 kilograms of wafer grade silicon by 2040. So there's a clear mismatch here, and there's a need to discover new storage technologies. And one of our targets is 100x storage density improvement. Next slide, please. Next slide, please. So seismic shift number 3, the data communication gap that David briefly mentioned at the outset. So there's if you look at the red curve, that's the data produced in terms of zettabytes per year. And the blue curve is our capacity to communicate this data. And you can see the two charts meeting and diverting. And the difference between the two charts is growing over time. And that's what makes this a seismic shift. So there's a need to develop new communication technologies to move around all stored data, 100 to 1,000 zettabytes per year at a peak rate of 1 terabits per second, consuming less than 0.1 nanojoules per bit. All right, next slide, please. Seismic shift number 4, ICT security challenges. And I'm going to come back and talk more about this seismic shift. But to summarize what you see here on this chart, basically there's a trend in recent years that the growth rate in the vulnerabilities on the security side, they're growing faster than the performance on the compute side, right? And that's a very alarming trend. And I will come back and visit this a little later in the discussion. Next slide, please. Seismic shift number 5. Right. If you look at the chart, the orange line is the total world energy production. The green line is the proportion of energy consumed by ICT. And you can see that if current trends continue, that ICT is taking a bigger and bigger and bigger portion of the total world energy production, and we simply can't have that. We simply can't have that. We have to find new architectures, new technologies that can address this. This is, one of the most alarming trends of the 5 seismic shifts. So, compute will not be sustainable by 2040 because the energy requirements are expected to exceed the estimated world energy production. I know this is a big statement, but the data is there and the data is clear about this. Right, next slide, please. So the Decadal plan is calling on fundamental change in thinking, from novel materials to novel ways to look at security, private, and trust. Next slide, please. All right, on the communication side, let's focus a little more on that side now. Next slide, please. All right, so 2 grand goals for communications. I briefly talked about them earlier. So the first one is that we need to advance communication technologies so that we can move around all stored data, which is estimated to be between 100 and 1,000 zettabytes per year, at a peak rate of 1 terabits per second, consuming less than 0.1 nanojoules per bit, right? And the second goal is that we need to develop intelligent and agile networks that effectively utilize the bandwidth so as to maximize the capacity of our networks. Now, there are a number of grand challenges. First, today, there's no clear path that we can see in terms of enablers for 6G. There are fundamental limits for wireless communication. And the idea there is maybe we should bring back the physics into the communication equation. For example, looking at Einstein's quantum framework, which is based on photons, that may offer new insights and may become a useful complement to the classical Maxwell's equations, looking at anticipated thermal challenges, passive elements based on physical mechanisms. And so the idea there is, let's bring back the physics into this. Communication energy per bit, I'm going to show a chart on that a bit later, and security. Key topics that the communication chapter in the Decadal plan addresses include millimeter wave trends, power, quantum internet possibilities, what life after 5G might look like, a vision for possibly performing a global multi-target optimization with machine learning. Can we borrow from biology, for example, on the security slide, and I'll talk a little more about that later, and some novel research pathways. So I encourage you to download the Decadal plan and read the communication chapter. It's rich with information, rich with ideas and challenges. Next slide, please. All right, I talked about, one of the grand goals for communication is on the energy side, 0.1 nanojoules per bit. And what this chart shows you is a breakdown of the ICT contribution on the energy side. So if you recall the initial slide, which is seismic shift number 5, shows you the total ICT energy in terms of joules per year. And how it relates to the world energy production. This breaks down the ICT into the compute. So a graph on the compute side and a graph on the communication side. And you can see from this chart why we are worried about communication energy per bit. So even though it's not a problem today, but because of the sheer volume of data that is produced and doubling on an annual basis globally, eventually the communication energy price is going to exceed that of the compute, right? And that is possibly a very dangerous development, that the communication energy will exceed the compute energy. So something has to be done there to lower the compute energy per bit. Next slide, please. All right, so I talked about security. Security is a separate issue that we discussed in a separate webinar. It's a separate seismic shift, but it's not completely separate. I mean, you cannot think of communication and security separately, right? They go hand in hand. In fact, you can think of all the seismic shifts as being intertwined and interrelated. So on the security aspect of communication, right, the idea is that we need to think of security just like we think of safety. And I apologize to the people that like the 737 MAX 8 Boeing airplane. I'm using it as an example here because software security cannot be an add-on to the hardware side. So we cannot think of security as an add-on on the software side. We feel that security has to be built into the hardware. Future communication systems must be designed for security from the ground up. Now, some data for you. Recent report from a US interagency technical guidance report found that on average, there's 4,000 ransomware attacks happening on a daily basis since 2016. And a recent report shows the data that's in front of you. These are 2020 data, 5.6 billion malware attacks, 4.8 trillion intrusion attempts, over 300 million ransomware attacks in 2020. That's almost 1 million per day globally, right? And something related to that, a study found that 75% of attacks of companies that were surveyed were actually successful ransomware attacks. So a significant proportion of these attacks are successful. So what does this all say? What it says to me is that we're failing. We're already failing on the security side, right? So this is truly, truly something that has to be addressed. If we're already failing, and if you go into the future 10 years, 15 years from now, and imagine the data explosion that we will experience by then, and given that we're already failing on the security side, something fundamental has to be done on the security side. And one question that was raised in one of our workshops about a year and a half ago was, can we learn from biology? Next slide, please. So our bodies have an amazing built-in proactive defense system. And I'll just mention one aspect of it, which is part of our adaptive immune system. We have T cells that are developed in the billions in our lymph nodes with every possible receptor combination. Let's call it connector combination. And so these connectors on our T cells can connect to every conceivable virus that has come in the past, may come in the future, or much later when we go to Mars, right? So our body has designed billions of combinations of T cells to address any conceivable virus that can happen, right? And the way it does that is that we have dendritic cells that go into our lymph nodes. When it finds a virus, it looks for a T cell that has the right connector and tags it along to attack the virus. Now, this takes a little bit of time to do because the search is done probabilistically and randomly through our lymph nodes. But the design between the innate defense system and the adaptive system is truly amazing, and maybe we can learn from it in terms of designing our next security systems. Next slide, please. So, big picture summary: future of communication driven by intelligent edge nodes with local analytics, requiring new modalities for security. I truly feel that security and communications have to be addressed together. With no clear pathway towards 6G, and we must have a holistic, multi-objective vision that brings together energy, security, quality, performance. So seismic shifts, all 5 of them, in my mind, are very much intertwined. Next slide, please. And even though the Decadal plan tries to influence, government funding and university research, I think there's a role for venture capital and startups to play in this area. If you look at the funding coming out of venture capital, funding related to the internet in the first quarter of 2021 was over $25 billion, first quarter of 2021 on the internet side. In terms of mobility, it was over $10 billion. So there's a lot of funding in the VC world. Andreessen Horowitz have developed a vision for Web 3.0 that is decentralized and distributed, open, inclusive, participatory, resilient, sustainable, efficient, and secure. And I think there are opportunities for the Decadal plan and the Decadal Planning Committee to explore synergies and possible collaboration with the VC world to increase the funding going towards fundamentally different research. Next slide, please. And I'll end with this slide. The Decadal Planning Committee has been publishing a series of blogs on the Decadal plan. Last August, we published one on the communications seismic shift, which I urge you to take a look at. And you can find these blogs under Victor Zhernov's LinkedIn webpage. Thank you very much.
Thank you very much, Dr. Mackey. And that, I hope everyone can hear me. With that, we are moving on to our next segment of the webinar. My name is Lu Yuan, and I work for Qualcomm. So this is a roundtable discussion session for future communication technologies, and I will be the moderator for the discussion. We're glad to have the industry, academia, and government experts joining us today to share their insights and answer our questions. I'd like to introduce the panelists today. They are Dr. Gabriel Magnardo, Director of Technology at MediaTek, Professor Gabriel Ribes from Electrical Engineer and Computer Engineering Department at UCSD, Dr. Peter Gamel, Vice President and CTO of the Mobile and Wireless Infrastructure BU at Global Foundries, Mr. Guy Aristov, Senior Vice President, Chief Strategy Officer at Tower Semiconductor, Dr. Marla Dowell, Director, Communication Technology Lab and Older Lab at National Institute of Standards and Technology. Welcome, panelists, and thank you so much for your time sharing your insights with us here today. So in the next hour or so, we will first ask each panelist to give a short talk. For the audience, you're welcome to submit questions through the Q&A window that's at the bottom of your menu bar at the Zoom window. Named the Q&A. Just a note, it's not a chat window, it's a Q&A window. And we will have the panelists answer questions after all 5 panelists' presentations. So if your question is directed to a particular panelist, please mention that in your message. In the end, if we don't get to address some of the questions during today's webinar, the panelists will answer them offline and they will be posted on the event page a few days later. So let's get to the talks. So first, Dr. Gabriel Magnardo will start us off with his talk on high aspirations, plenty of technical challenges ahead.
Hello, and thank you for the opportunity to be here. Next slide, please. So in the previous presentation from Dr. Rafik Mackey, you have seen that there is certainly an increasing gap in terms of the amount of data that needs to be communicated and the capacity of our communication technology to actually deliver the data. And one thing that I wanted to say up front is that unlike what has been popularized for the most part so far, which is that the increase in communication, it's mainly driven by higher speed, higher throughput. This is the way it's been often presented. You know, you can download a movie in so many few seconds and so on and so forth. This is certainly a trend, but the applications that will drive this gap between the amount of data and the data that needs to be communicated, they're going to be actually very diverse. There are going to be some applications such as artificial reality, virtual reality, and others, which will, of course, demand with higher and higher throughput. But there will be other different applications which are going to be very different, where it's not about a higher throughput, but it's going to be about the higher number of connected devices, the number of devices that will compete to be able to communicate, the UEs, the user equipment, that they will try to access the access points, the gateways, etc. The number of these devices will be increasing dramatically, and therefore will drive a higher needs for communication capacity. And in addition to that, there will be also other applications where it's really all about the latency, the ability to promptly and deliver the information in a timely way, very quickly. Next slide. So in addition to this wide diversity in driving applications, there will also be a confluence between communication technologies and computing technologies, and an interdependence between them. In computing, there is paradigms like cloud computing or fog computing, where the compute is happening in a localized. It's happening in certain data centers, etc. And then there is a very different paradigm where, in fact, computing happens localized where it's required. That's edge computing, and just like that. Also for communication technologies, we will have different models, and the communication technologies and the computing technologies will work together in an interdependent way. And as also Dr. Mackie has illustrated earlier, all this increase in communication and in the amount of data, inevitably, it's gonna come down to affecting energy consumption. All of this, of course, requires energy, and the demand is only going to increase, which obviously creates problems, several problems, and questions about sustainability. So that will put certainly a lot of stress on efficiency in which we accomplish all of that. And of course, present solutions are not gonna support this indefinitely. So this requires new solutions, and it requires holistic solutions. Thank you very much.
Thank you, Dr. Magnaro. Next, we move on to Dr. Gabriel Ribes from UCSD. Please go ahead.
Thank you. I'm going to talk here more about the communication aspect. And this is a chart that I presented maybe 7-8 years ago, where I noticed that the communications, our communication systems, and that was when LTE was there, even though we started using many frequencies, but from an antenna point of view, we have not changed anything since 120 years. That's 1900 Marconi. You could see the base station on the right, and these two long pieces of metal is the base station antenna. And then you could see the receiving device on the left, and that you would consider your cell phone or your dipole. And we were effectively a omni antenna, broadcast omni antenna, to a broadcast receiver omni antenna, like a cell phone. And up to 2010 and 2015 and 2017 and so on, when we looked at base stations, we would see that base stations are foremost omni. Yes, they are sectored today, but they are omni. And all receiving antennas are omni too, from a mobile phone to a car phone to a wireless LAN to your computer, wireless LAN, everything is omni. Now, why have we done it? Because it is easy. That's the reason. I don't need to know where you are. You don't need to know where I am. I just broadcast and then you receive. And the same thing, by direction. But it is very inefficient. I take a lot of space. I take a lot of spatial space. I spread energy everywhere. So it results in high interference and, in general, a much lower capacity system. And the whole point of 5G, 6G, and the future communication is how to improve capacity very much because of the talks that you have heard in terms of data usage and biological and how much data we generate and so on and so forth. All what you have heard from Dr. Mackey and Gabrielle, even IoT devices, we need to improve capacity. So let's go to the next slide, please. Well, how do we improve capacity? We basically, when you look at channel theorem, when you look at the communication, theory, when you look at systems, there are effectively 4 ways to improve capacity. One is easy, and it is more bandwidth. Well, FR1, sub-6 gigahertz, 3.5 gigahertz, 5 gigahertz, 6 to 7 is all about more bandwidth. FR2 is all about more bandwidth. Rather than having 20 megahertz here, you have 200 megahertz. Rather than having 40 megahertz here, you have 400 megahertz, and so on and so forth. And FR3, which is now being proposed, is also to communicate at 7 to 20 gigahertz in certain channels which are pretty wide. But the other is basically spatial diversity, which is directive communications. And that is how do we make phase arrays, multiple MIMO streams, lots of simultaneous beams, analog beamforming and digital beamforming. And now I have a pointed beam that's pointing to you, and I'm not spraying energy everywhere. And of course, I can do multiple beams and multiple coding in order to have a 4x4 MIMO and other systems. The third, which is also tied to very much like the second, is better coding and channel modeling. And 5G is all about coding. I mean, from MIMO to channel sounding to adaptive nulling to reduce the interference to DDD rather than FDD. And the last is a great advancement in devices for both low noise figure and better PA efficiency, because all of these are based on arrays, on large antenna apertures. Even at sub-6 gigahertz, they are large antenna apertures and require a lot of devices, and we need to have a ultimate lowest noise figure and very good solid state PA efficiency. The only thing that I say to the 5G community, and I have said that since about 10 years, is that all of this, every single one of this, was well known by the satellite community. And the satellite community, since 20 years ago, was building 200 to 300 simultaneous beam systems, which we call geosatellites. And they were placed at 36,000 kilometers. And I want to point you out to this picture of I think it's a Jupiter 21 Hughes Network Systems, or one of these large satellites, and it's built by Loral. And see the satellites and see the humans. These two white things underneath, all of these white things underneath are actually humans. These satellites are larger than city buses, yellow school buses. And we actually will put them at 36,000 kilometers, do 300 simultaneous beams from them, and do 1 terabit per second today. And Viasat-2 and Viasat-3 and Intelsat, and SES, and so on and so forth. So we knew about this, but it was expensive, and these satellites costed $500–600 million. And now with 5G is that we are applying it at a massive scale, to have it on every base station, which is 300 meters to a kilometer away from you, at both sub-6 gigahertz and millimeter waves, and effectively to apply all of these fundamentals, which is bandwidth, spatial diversity, coding, and better solid state noise figure and PA efficiency in order to increase capacity by 10 to 30 times. And we have to do it. We have no choice. So I finished by saying anything that can be done with phased arrays will be done with phased arrays. That's a given. The system gain and implications are too large to ignore. So you could say it as a dictum, but this is it. If you can afford to do it with a phased array, being analog, digital, MIMO, multiple beam, you will do it. And I close here. Thank you.
Thank you very much, Professor Ribetz. Next, we are moving on to Dr. Peter Gamel from Global Foundries, and his talk is on silicon technologies for future wireless communication networks.
Thank you very much. Next slide, please. So I want to build a little bit on what we've already heard from UCSD and MediaTek, both of whom are fantastic partners for Global Foundries, and drill down and look at the semiconductor roadmap and the technologies that are going to be needed. And I'll look at two aspects of this. One is just in terms of the network topology, and the other is in terms of the frequencies and bandwidth, and really focus here on the wireless parts of communications. So we already heard that there's an opportunity to evolve the network into more of a, we heard it as a seamless, multi-protocol, always aware network, perhaps moving from the two-dimensional topography to a three-dimensional. And certainly here, and then we already heard from Gabrielle, enormous growth and enormous opportunities in the non-terrestrial piece of the networks. The geo satellites that Gabrielle mentioned, evolving to arrays of LEO satellites. The most frequently in the news are, of course, the SpaceX Starlink, which just a mile or two from my home is already showing a 200 megabits per second connection, as well as the Amazon Kuiper, where we saw the announcement even yesterday with a combination between Verizon and Amazon looking to provide worldwide and global network coverage. As perhaps we didn't mention it here because we were so focused on high-speed data, but there are still multiple billions of people who have no network access at all, and the ability of networking and data access, as Rafiq said, is what gives you access to the modern world. So definitely seeing enormous growth in the non-terrestrial networks. This is being built into the roughly release 17 of the 3GPP. And in terms of the semiconductor devices, what does it really do? Right now, the big focus for us is on reducing the RX noise figure. And as I say on this slide, do you need to drive beyond silicon CMOS? Our view is that both silicon germanium bipolars, as well, perhaps even complementary bipolars, as well as silicon on insulator. And we've seen tremendous uptake of both our partially depleted silicon on insulator at the 45 nanometer node, as well as the fully depleted silicon on insulator at the 22 nanometer node, for communications frequencies up to 120 gigahertz with outstanding noise figure. And the noise figure really drives the array size, the cost, and the rapid deployment of these types of non-terrestrial networks. The silicon germanium and the SOI are both deployed in space today. I think one of the interesting things with the low Earth orbit satellites is actually some of the traditional concerns people had about radiation robustness, which is a big issue for the geo-type satellites that Gabrielle mentioned, is actually quite mitigated in the low Earth orbit. So we can actually use a lot of the technologies that we developed for low-cost communications in the low Earth orbit satellites in the silicon germanium, as well as the SOI nodes. Next slide, please. This is perhaps a little bit more controversial, especially when I talk to Gabrielle, but in general, we've seen that the base communication frequency as well seems to move up with the node of the G, and part of it is just the search for bandwidth. So if our overall data rate is just proportional to the bandwidth times the MIMO order, and fractional bandwidth is what's easier to design into, then kind of by nature, frequencies go up. There's been a lot of talk about 100 to 300 gigahertz, where there's a lot of spectrum available, and people have shown that you can do reasonable communications. And I saw a nice email from Gabrielle last night about their demonstration vehicles using some of our technology at the 140 gigahertz band. But in general, push to higher frequency. Higher frequency not only enables higher frequency communications technologies, but also improves the efficiencies of the devices. I show here from Hua Hong the chart on the upper right about the PA efficiency tailing off dramatically as you go to higher and higher frequencies. And one thing that you can do about that is to improve the FT and Fmax. I also want to point out that, again, echoing what was heard earlier today, we see a lot of push to the 100 gigahertz and above. But I do want to point out that what's called FR3, the 8 to 20 gigahertz spectrum, above what we're using today, which is pretty much sub 7 if you include the 7.2 Wi-Fi, is really ideal communications bandwidth. And if there's one thing I want to advocate for within this forum, is to lobby our regulatory bodies and industry alliances to accelerate the use of the 8 to 20 gigahertz for communications, where there is plenty of bandwidth available. It's a good in terms of device technology, communications theory, modulation order, linearity, but is already heavily used and will require quite a bit of work. But if we're looking at a decadal plan, now is really the time to start laying the groundwork to open up that spectrum. In terms of semiconductor device technology, if we look at the chart on the lower right, which I've shamelessly taken from John Strange at MediaTek, and I know we have other MediaTek people on the call today. For a long time, just as we followed along CMOS scaling, we naturally got an improvement in radio frequency technologies, kind of to the 45 nanometer node. But somewhere around 45, FTs and Fmax tail off and then actually start to go down as you go and reduce your node in both CMOS and FinFET below something around 22. And that means you need a new type of approach other than the straightforward silicon CMOS. What we've shown today and we'll emphasize today is silicon germanium has an excellent roadmap to continue what we saw in CMOS. Today, you've demonstrated silicon germanium HBTs with FT, Fmaxes above 500 gigahertz. And there's a clear and well-articulated roadmap. And again, the type of funding that was mentioned by Victor and Rafiq to continue to drive the silicon germanium roadmap, you can achieve greater than 1 terahertz devices. So allowing G-band communications within the silicon germanium family without moving to the more exotic heterogeneous integration of indium phosphide or gallium nitride. DARPA T-Music was one example of that, but we need to continue the drive to improve devices to above 1 terahertz. That said, I think we'll hear later in the day, heterogeneous integration is something that needs to be considered, especially as you move to higher frequencies. That monolithic integration between the antenna, the package, the RF front end, and the high IF transceiver will be an incredibly important part of next generation communications network. So I'll hand it off to the next panelist, and I appreciate and look forward to the questions.
Thank you very much, Dr. Gamble, for your inspiring talk. And I just like to remind the audience that you may submit your questions through the Q&A window, and we will come to that after the next two panelists give their presentation. So we will next move on to Mr. Guy Ristow from Tower Semiconductors, and he will present enhanced RF devices and the photonic design platform to address hyperconnectivity growth.
Thank you, Lou. And well, thank you, Peter, for teeing me up, because one of the fundamental precepts of what I'm going to talk about today is heterogeneous integration. Peter was absolutely right. New materials and new integration technologies are required to drive the specialization and the differentiation that's needed to move to the next level in data transfer and high-speed data transfer. So in Tower, we're a foundry. We design transistors and process design kits. And those process design kits, go to customers that then design integrated circuits, come back to us. We build them, and then they're packaged up and given to customers. And looking at RF devices, there's a complement of different devices, and they're very specialized. And I'm going to look at them from the optic of PPAC. Now, PPAC is performance, power, area, and cost, because these are four things that I think most people can relate to, and they're four incredibly important components, as well as the figures of merit. So if you look at the terahertz wave that Gabriel Rebez was talking about for phased arrays and beamforming, we have developed some very, very good devices with very good figures of merit, but they're also, while the frequencies, F sub T's, F sub maxes are good, the area savings are very good from different layout tricks. Really, from a cost perspective, it's very interesting that the silicon germanium for base stations and for phased arrays seems to have a sweet spot compared to gallium nitride or RF-SOI. And one can notice this in the graph to the right in the NXP webinar that was given, I believe it was last year. But silicon germanium really has the sweet spot in terms of power consumption and cost, while still giving very good frequency responses. Now, if we move to something like handsets, a key critical component of handsets, especially in 4G, 5G, and 6G, the number of switches multiplies significantly because of the different frequencies that are required and the different number of front-end modules that are required. At the lower end of cost, so good from a cost and an area perspective, if the throw count is low, RF-SOI is a very good contender. And I'm sure Peter Gamble would agree with me on that. We both have very nice platforms in RF-SOI. But there are limits to RF-SOI in terms of power and performance. And then you can move to the next bullet down, MEMS. And MEMS have very good power handling and isolation. So power and performance are great. Area is rather large, and cost is pretty high compared to, say, RF-SOI. And then you have a PCM, so a phase change material switch, new materials. And this is the other emphasis of my discussion today, is that new materials are key, whether it's going from silicon to silicon germanium, or to phase change materials, or to, say, a photonic platform. Different new materials driving differentiation are important. And you can see the performance metric in terms of our on-C-off is an order of magnitude better than anything else out there. However, it's the power is a challenge, and the cost obviously is a challenge. But you can see the performance metrics compared in these three different types of switches in the multicolored graph on the right. And for insertion loss and isolation over the wide band of 0 to 40 gigahertz, really the PCM switch is the dominant factor here. So, silicon germanium, SiG, CG, however you want to call it, is very, very good for power amplifiers, especially small cell power applications, power amplifiers. Competes very favorably with CMOS, of course, and also from a cost perspective, it competes very favorably to 3.5 materials. And then silicon germanium by CMOS for multiple applications, wide variety of applications, really is a workhorse for us at Power Semi in terms of RF data center and RF communications. And the future is to combine very high gate count CMOS with the silicon germanium, either integrated at 6545 or going to 2.5D or 3D IC, as you see in the SEM pictures below, and bonding direct wafer to wafer bond. Next slide, please. photonics. There's been a lot of talk about photonics, and it's the communications medium that it's kind of the airplane, it never gets off the runway. And it seems like photonics is really taking off. We have a very nice photonics design kit. There are multiple other ones out there, but being a foundry, most of them, the design kits are integrated device manufacturers that design for their own parts. But with a foundry design kit, almost anybody can come and design photonic parts and then introduce them into the market. And it's really all about fidelity and losses in silicon photonics. Close coupling with PDK elements is fundamentally critical, and reducing the photodiode dark currents or the laser diode, the dark currents are incredibly important. And that's the drive really from germanium photodiodes to other types of material laser type diodes is dark current and fidelity and also speed. Depending upon layouts, you can see on these graphs a 3 order of magnitude reduction in the waveguide loss. So depending upon the layouts and the materials used, you can really tune the system to get incredibly lossless fidelity. In terms of photodiodes, just by a different layout change, you can change by up to an order of magnitude. And by a material and layout change, another 4 orders of magnitude in dark current. So it's all about new layouts, new differentiated technologies, and new materials. So the takeaways are certainly different technologies and platforms to meet specific power, performance, area, and cost, and other figure of merit requirements. And then monolithic integration, whether it is template layers, whether it's 2.5D chiplet on wafer, or whether it's 3D DBI or hybrid bonding. This is really the next generation of getting to the next level of speed and data rate. Thank you.
Thank you very much, Mr. Esthoff. Last but not least, Dr. Mala Dawah will talk about a position from NIST.
Thank you, and thanks for the opportunity to be speaking with everybody today. And as you heard from the previous speakers, innovation is needed to address these decadal challenges, particularly lots of innovation challenges in the communications areas. Measurements and standards are foundational to enable innovation, from assessing performance to accelerating design and materials discovery. And at NIST, we have a long history of communication innovations, actually dating back to 1908 and the first radars that were developed for the Navy. Today, our work focuses on measurement, standards, and innovation to enable reliable, resilient, and secure communications networks of today and tomorrow, including advances in connectivity and interoperability for powerful solutions in manufacturing, public safety, and infrastructure. In the limited time that I have today, I'd like to highlight kind of 2 areas of challenges of measurements and standards to enable this innovation. First, at the system level, there are system requirements which are driving technology advances. From the one side, looking at AI-enabled advanced communication networks. These will be highly distributed, fully autonomous communication networks where decision-making is focused at the edge, and data will be needed to assess and benchmark the performance of these networks. Why this drive? There are issues like reducing energy consumption, preserving data privacy by keeping data locally, and it can also lead to increased resiliency and reliability. So what's needed in this space? Things like wireless communications and edge learning in co-design research, validated open training data that is non-proprietary to advance standards across the industry. improved RF signal identification, and antenna optimization, beamforming, training, and tracking and scheduling. That's on the network side. Then there's on the application side, there's lots of innovations that are needed for autonomous systems. You know, what are these? It's from the electrical grid, the smart grid, smart manufacturing applications, smart buildings, autonomous transportation. You know, why is this needed now? Well, today we have within reach is the issues of our operational technology, making decisions without human involvement. However, there are issues needed to improve the resiliency, reliability, and even the security of that operational technology. And all you need to do is read the newspapers today to see concerns about the use of operational technology in water distribution and other sort of infrastructure type issues. So what kind of advancements are needed in this space? We need cybersecurity countermeasures for operational technology systems, measurement-based approaches to identify counterfeit hardware. We can't rely on human intervention alone to address these cybersecurity challenges, nor can we just take a defensive posture here. We also need higher bandwidth, lower latency, autonomous communication systems, those AI-enabled networks to support these application space. Next slide, please. At the other end, so we talked about the system level, all the way at the other end is device level measurement advances that we need. In particular, you heard some of our speakers talk about 3D heterogeneous integration. You know, why is this of interest now? Maybe I don't need to revisit this, but things like increased integration density and functionality, the opportunities to use new materials, the opportunities to reduce power, cost, and latency. But what's needed now, if I look at a heterogeneous structure like this figure that I've shown here, is we have to be able to evaluate these chips at each of these levels. We need to be able to evaluate the interfaces. There are measurement challenges at the interfaces between these chips and materials buried in multi-layer stacks. We need to have new measurement techniques that address not just the individual chip level measurement challenges, but also how they integrate together. We also need new models to evaluate dynamic 3D systems. And we need things like electromagnetic, thermal, and mechanical properties and constituent materials to address, to go into these models. And it looks like the bottom thing is cut off here. The other thing that we need is also not just those static materials properties, but we also need dynamic or the broadband RF response of these devices too at each of these levels. And so at NIST, we're working on many of these challenges, and we're also working with organizations like SRC, INEMI, and other manufacturers to work on the measurement tools to address these challenges. And with that, I'll just sort of stop so that we have plenty of time for questions. Again, thanks for the opportunity to speak with you today.
All right, thank you all panelists for your inspiring talk. And with that, we move to the Q&A sessions. And I'll address the first question to Dr. Magnaro. You have hinted at some of the applications that will drive the new communication technologies. So would you like to expand a little bit more on the application side?
Yeah, so as I was saying, there are going to be some applications that are going to drive the need for higher throughput. And examples of that are artificial reality, virtual reality, telepresence at some point. There is some discussion at some point in the future, even holograms. So those are going to require a really a real increase in data rate. So today, we are in the order of the low tens of megabit per second as a data rate, with peaks of the order of a couple of gigabit per second. In the future, if we really need to be able to implement applications such as even holograms and or really very immersive artificial reality, virtual reality. We're really going well into the data rates of the order of gigabit per second, with peaks nearing the terabit per second. So those applications are really going to demand for an increase in throughput for few users. That's one kind. But there is a completely different kind of set of applications that are going to drive instead a need for higher capacity because of the number of UEs. So I'm referring to the Internet of Things, the Internet of Everything, and that includes a variety of different things, from autonomous driving. It includes healthcare applications, robotics, Industry 4.0, where really the number of devices is exploding. So today we are talking about something like 100,000 of devices on a square kilometer. In the future, this could go 10x higher. And so it's not that these devices necessarily demand a higher data rate. It's that the number of devices that is increasing. And then there are going to be different applications, such as some specific industrial applications in robotics, in industrial automation, or even some very specific applications in healthcare where to an extreme, you can imagine remote surgery, where you actually need the latency to be really, really small in order to react very quickly and not to have catastrophic events. You can imagine an intervention where a car is on a collision path. And so you need to immediately communicate with the server, or if you're doing surgery, or if someone is having a heart attack. So today we're talking about latencies of the order of tens to a few milliseconds. In order to enable these applications, the latency needs to go down to a millisecond or less, or otherwise just the application isn't feasible. So that's really a variety of requirements that is very diverse and drives completely different specs and completely different enabling technologies. Yeah.
Thank you, Dr. McNarrow. Let's hear more from our panelists on insights on how to address the challenges we will face to enable the diverse applications. Mr. Aristov, I was wondering whether you could share with us your thoughts on the bandwidth challenges with applications mentioned such as AR, VR.
Yes, and I think Gabriel is exactly right. AR, VR is a huge challenge to get a credible, enjoyable experience that looks good for a 20-year-old's eyes. A 20-year-old's eyes have such a resolution that the angular response and the need for pixels at 4 microns or below are required just due to the layout of the goggles. So you're talking approximately 230 megapixel displays, one on each eye, 60 to 120 hertz or cycles per second frame rate, 14 to 16 bits of color depth. And that amount of data needs to be traveling to a PC and back, because a PC, a high-end PC, is the only thing that can handle this, and even that's challenged. There's no wireless except for massively parallel wireless capability that will allow, and even that will allow you to do that. So right now, for not having artificial objects, screen door effects in front of a person's eyes, you have to be tethered from a communications perspective. The power requirements are so great for micro LEDs at those, the power of, and so many micro LEDs that you have to be tethered or have a huge battery pack on your back, or you have to be tethered into a fixed power supply. So there are some real problems that both from a power perspective and from a bandwidth perspective need to be taken care of or catered to if we're ever going to get good good VR and certainly AR, and reducing that to something where you have overlays of augmented reality with through, say, a transmittable semiconductor, so an ultra wide bandgap semiconductor, gives its own challenges as well. Not so much in the bandwidth, but there are other challenges that need to be worked out, especially in power performance, to allow AR, VR to become something that is more than just an amusing toy. So there are huge leaps in both of these areas that need to take place in order to have a credible system going forward.
Thank you very much. And I would like to ask Dr. Gamble, would you talk more about challenges with the always-on connectivity aspects that are required by applications such as low Earth orbit satellites, drones, urban wireless, and fixed wireless, etc.?
Yes, I think in general, let me rephrase that and think the most obvious case of always on communications, which is your mobile device, right? Mobile devices are moving from a place where you switch them on to where they're always listening and always watching and always communicating that data back to the network. That means you need the low, we already talked about the low energy per bit and the seamless multi-protocol network. One of the things I think people don't always associate, because we have a lot of talk with IoT and the high bandwidth, but in order to have the lowest energy per bit, it means really you translate that backwards, you should be transmitting at the highest power and the highest data rate in a very low duty cycle environment. So in our view, these two things are heavily correlated. The other thing that we really see, and this drives that low energy consumption, is in the very near future, your communications device, the UE, is likely to split into 4 unique devices. Right now, you have one mobile phone that does everything, but where our anticipation is that will evolve into a communications hub, the mobile phone, paired with glasses, paired with hearables, and paired with a watch. And we can say, well, what happened to your other 2 senses of taste and smell? And I'm not going to comment on that. But that data will need to be seamlessly transferred between those 4 devices, which is also a very high bandwidth and low latency. One of the places that drives what we heard earlier about the low latency is if you want to have your human mind sync between video and audio coming from different sources, that actually drives a latency in the sub-millisecond regime. So the 2 things are, you want low energy per bit, that means transmit fast and at high power. And the transition to always on is here, already here in your mobile device. As that moves to the network implementation, our expectation, as many people have said, not only will you see this multi-protocol sort of Gaia-like network involving satellites, Wi-Fi, 5G, everything, you'll move to the multi-mode, multi-protocol network. And again, in this environment, one of the things that seems to never get resolved, but I think we should get the SIA, SRC involved, is IEEE and 3GPP can never seem to get their act together to figure out how to do seamless handover and seamless communications. I asked MediaTek about this in an internal call yesterday, and they said, well, we've been talking about it for 6 years or 10 years and seems to still be going nowhere. But that need to drive the seamless multi-protocol network is absolutely there. Thank you.
Thank you very much. Next, I'd like to ask Dr. Dao. Could you please comment on the challenges we face with the explosion of diverse forms of machine-to-machine communication systems?
Yeah, so this is a real question about interoperability and reliability. And that's where standards and measurements can both come to play. Things like having Wi-Fi and Bluetooth devices in the same environment. And there are some environments where we have to worry about coexistence issues, like a healthcare environment. So this is an opportunity where data is needed for us to evaluate how well things are performing and to have uniform sort of descriptions about what are interference issues, how do we define that. There are some work on standards in that area, but most oftenly it's just looking at one segment, which is just Wi-Fi only, Bluetooth only, 5G only, and we really need to start looking at the whole communications ecosystem.
Great, thank you very much. Then I'd like to come back to Dr. Magnaro. Could you address the proliferation of applications with ultra low latency? What is the ultimate limitation?
So, so latency comes from different parts of the entire stack. Of course, there is some of it that is originating from the physical layer, some of it from the MAC, but the one opportunity to reduce that has to do with the transport layer, and specifically the TCP/IP, which has been there for generations. It's been there since 2G. And it was there in place to guarantee QS, quality of service. Now the technology has improved over time, so there is an opportunity there to simplify, flatten, and work on the transport layer and reduce the latency. Of course, as I said, that's not the only place. There is some of it coming in the physical and some in the MAC, but that's definitely one place where it's that is ripe for innovation.
Thank you very much. I'd like to address our next question from the audience to Mr. Aristov. So gas for opto micro LED is progressing to 8 inches and mass production expected in 2 years. Maybe RF gas can also enjoy this benefit and with finer process node to compete with silicon germanium for higher switching frequency. What is your thought on that?
Well, first of all, I think you may be mixing gas and GaN, because for micro LEDs, the flavor of the day is GaN, either using a miscut template layer, germanium template layer, and fully integrated into a CMOS, or either doing 2.5D or 3D bonding, as I talked about before. Now, moving to 8-inch, with what you're talking about, it sounds like that's template layer approach, which has been widely worked on in academia and is now just coming to the forefront in 8-inch. And I agree with you, that is important, and it will drive larger and larger micro displays. I also agree with you, now switching to gas, and maybe Peter would like to comment on this a little bit, as he's more of an RF expert on devices than I am, but switching to gas, certainly going to 8-inch has large cost benefits, and using a similar type of technique so that you can get a lattice match device, it could reap some serious benefits. Peter, would you like to continue?
Yeah, thanks for that opportunity. I think, again, when we look at the future of radio frequency technologies, I liked what Guy said. You know, we need to start looking beyond silicon at new materials. Both major wafer foundries are heavily developing silicon on insulator as well as silicon germanium. And all of us are looking at gallium nitride. And there are two approaches to this, either wafer to wafer bonding at 12 or 8 inches, or collective die to wafer, as people are doing in the micro LED market. I think we need to look hard. I don't want to pick winners and losers. Clearly, gallium nitride has some significant opportunities for both the power device as well as the switch. I know people are looking very hard at not only gallium arsenide HBTs, but indium phosphide as well, as you try to push and increase the efficiency at high frequency. One of the things I didn't even show, but was kind of implicit in Hua Hong's chart, is radiated efficiency from a mobile device is in the low single-digit %, right? Especially for today's millimeter wave communication. So, the challenges we're seeing around global energy consumption is fantastic, and I know we need to work on it, but the poor battery in your mobile device is kind of what I worry about every day, and how we can improve that radiated efficiency. We're driving our strong roadmap, but I think everybody needs to look at these new heterogeneous integration. And once you have that platform, the opportunity to bring in compound semiconductors of a variety, be it gallium nitride, which I believe, and you echoed what you said, I think that's the leader. But the opportunities for either gallium arsenide or indium phosphide. And honestly, once you're doing collective die to wafer, whether the base wafer for that technology is 4-inch, 6-inch, or 8-inch, doesn't really matter. Most of these things don't have die size matching, so wafer to wafer bonding is probably not the approach for these complex systems. I want to point out that many of our customers are not that far from that. If you look at the complex multi-mode module that's already in your mobile phone device, there are 4 or 5 different technologies, die stacked on both sides of a laminate substrate. They're not very far from the types of 3D integration that we're talking about today on our aggressively moving towards how they can put all those technologies into a single wafer. The one part that we don't discuss enough when we talk about that, and I know my old company is very aware of it, is what do you do about the piezo filters, right? Because we know a lot about what to do with power amplifiers and switches and controllers, but the piezo filters are something that, especially in the sub 7 gigahertz, you need to pay significant attention to, and how that integrates with the rest of the technology stack is still a bit of an open question in my mind. Thanks very much. And thanks for the handoff from the two foundries. We compete, but a lot of the vision is very, very common between us.
Thank you so much, Peter. Thank you, Guy. So we have a few minutes left, and I'd like to close it off with asking our panelists to help define a set of skills and talent requirements for our next generation of communication system developers. I'd like to start with Professor Rebes.
Well, it's integration. It's integration on chips and integration in packages to mix technologies. First of all, to get higher performance chips. Second is to mix technologies. So for me, at least at the physical space, it is going to be antenna arrays and lower power, better performance RF chips, and integration in packages of multi technologies, including filters and gallium nitride and CMOS and whatever is needed in order to arrive to the best efficiency and the lowest noise figure, and also low cost. I am not afraid of integration, of multi-chip integration. It has been pioneered by DARPA, then taken over by the commercial industry. And as Pete Gamble said, in your cell phone, the modules contain 5-6 technologies. So for me, it is really integration at the chip level and at the module level that's going to push us forward, and antenna arrays.
Thank you very much. Dr. Dao, I was wondering whether you have anything to add?
Yeah, so I'm gonna take a slightly different tact. I agree with everything that Professor Rabiz said about kind of the skill sets that were needed. But I'm gonna say from a bigger picture, we just need more, right? Right now, there are so many open jobs in this space, and we lack the technical skill set of the workforce, or the pipeline, is not there. So we need folks who have expertise in materials. We need folks who have expertise in EE. We need folks who have expertise in data. And the way that, at least in the US, the education system is set up today, if you want to major in engineering, you have to have calculus in high school. So just think of that. We are already putting a throttle on the pipeline at the high school level because of some of these requirements. So looking at programs that bridge the gap between what kids are learning in high school and what they need to be set up to succeed to be in these programs where we need them to be in college. I think that's one gap that needs to be addressed. And then the second gap outside of the classroom is we need to expose these early career folks to working and research environments. I think all of the folks on these panelists right today have internship programs. So I would love to see those internship programs expand, because at the end of the day, it's not you getting an A on a test, right? It's solving a problem in either a manufacturing process, a measurement process. We need people who are problem solvers, who can think outside of the box, who can solve problems that aren't in textbooks. And the way that you do that is by providing folks with those real world experiences.
Thank you very much. Thank you very much. That's very thoughtful. And with that, thank you everyone for attending today's webinar. And thank you all panelists for your time and for your inspiring talks, and get us excited about the opportunities and challenges with the future of communication technologies. And as we mentioned, we have some unanswered questions, and they will be addressed in the event page offline. Those will be posted a few days later. And with that, we conclude today's webinar. Enjoy the rest of your day. Thank